So we are going to consider perturbations. Yeah, so suppose y is an optimal candidate, you can call it y star if you like. Consider a perturbation g. So y plus alpha g is what we shall have. So if you put y plus alpha g here, what happens to this integral? X doesn't change, this gets replaced by, what happens to the third term? What will this get replaced by? Y prime plus alpha g prime, exactly. Okay. So now if you expand this in a Taylor series, of course it's a multivariable Taylor series, the first term doesn't get perturbed. There are three arguments in this, isn't it, in this Lagrangian. The second term will of course have terms related to alpha and higher order terms, and the third term also will have terms related to alpha and higher order terms. So this will essentially be a to b x y y prime plus integration a to b alpha times what exactly? Second argument gets expanded. What gets pulled out? G gets pulled out. When you expand the third one, what gets pulled out? G prime gets pulled out. Yes. But in the process, what else do you have to write? You can write the partial of this L with respect to its second argument and the partial of this L with respect to its third argument. That's what the Taylor series would entail. So I'll just use subscripts for those partials. When I write L with a subscript y, it means I'm taking a partial with respect to the second argument. When I write L with a subscript y prime, it means I'm talking about the partial of L with respect to the third argument. Okay. So this is L with the second argument, that is y x y y prime with a g plus x, of course this is with the third argument here, yes, y y prime, and you get g prime pulled out. Can you quickly take a look at this, bearing in mind that this is nothing but and of course additionally you will only have higher order terms in alpha. Yeah. Of course you might say you can also consider the alpha g here, but we'll eventually let alpha tend to 0, right. So can you now quickly tell me what is this object here evaluated at y along the direction of g, using that idea of the Gauss derivative that we've just introduced a while back. It is going to be this minus this divided by alpha, limit alpha tending to 0. So this by alpha will go to 0 anyway. What you will be left with is this, not a very impressive term as of now. In fact, a pretty clumsy looking term at this point, right? You have to equate this to 0. Doesn't convey much meaningful consequences, isn't it? Okay, it's just another function. But we're going to now do something here. I want you to appreciate that this is a condition that is pathwise condition. You're integrating over the entire path from A to B, the entire length of the curve from A to B. So this is a condition that is given in terms of something that happens to the entire path from A to B and equated to 0. So a condition that's a global sort of a condition. Yes? A condition on the entire curve. These are usually more difficult to verify. Yes? Let's take a look at the second term here. If you know nothing about how this is originated, and if you look at something like this, what is the first thing that you will be tempted towards doing? Integration by parts. Fantastic. Because this, integration by parts, we have this integration u dv is equal to uv minus integration v du, and that dv part is clearly being suggested by this bit here. Yeah. So let us try to do that here. This is going to be L with respect to the third argument x, y, y prime, g of x. But here's the deal clincher. Why is this important? Or why is this interesting? What do you think? Exactly. We've just argued a while back why g must vanish at a and b. Otherwise, y plus alpha g will not even be a legitimate curve that meets the terminal constraints. It can do anything whatsoever in between a and b, but at a and b it must be tied at the ends. Yeah. What about the remaining term? This is d dx of L y prime x y z dx. So this term, is it clear to everybody why this term is 0? Is everyone clear on why this term is 0? If not, please ask. The source is that g is some perturbation added to f or y. And at the terminal points, that is at a and b, the perturbed curve and the actual curve must agree. So therefore, the perturbation must vanish at the terminal points, because at the terminal points the curves are precisely known. In between, you have the flexibility to play around with different families of curves in the neighborhood of the original optimal curve. So this part simply vanishes. In view of this, we could very easily now write that first variation evaluated at y along the direction of g to be equal to a to b. Oh, I think I've missed out the y here, right? Yeah, sorry, I had missed out the y here. Okay. Now what happens? It carries with it a minus sign. Minus ddx of Ly prime x y y prime. I'll put this all in a box bracket now, because now earlier this came with a g and this came with a g prime. Now they are both accompanied by g. Yes, and this object now has to vanish, and you might still be wondering as to why is this better than the previous one. Well, one way it is better is because now we have a common factor to pull out of here, but that alone itself still does not solve the main issue we had with that expression. The fact that it's a condition that's laid out for the entire path, entire curve, right? It's a kind of a global condition and still not very convenient to check. But here's the final piece in the puzzle. This has to be true for all possible continuously differentiable functions g. And just entertaining a little bit of wishful thinking, it would be really nice if this essentially boiled down to the condition that this part within the box bracket were forced to be 0. What I am saying is, this condition, this integral being equal to 0 for all possible continuously differentiable functions g, if by some means this translated to an effective condition which stated that this thing that I have boxed here in this red box has to identically vanish at every point, then bingo, we have a condition that is now pointwise true. Not a global condition over the entire path, but a condition that has to be satisfied at every point of that optimal curve, and that is relatively easier to check. This is always true of differential and integral constraints. Integral constraints are like path constraints. Differential constraints are like pointwise constraints. Yeah, since we are dealing with reasonably smooth functions, y and g are all continuously differentiable functions, it would be rather nice if we had some pointwise conditions to check. So just indulging in a flight of fancy, if we can now establish that this thing inside this red box has to identically vanish, that would be a really nice thing to have at our disposal. But is it true? Just because we wish it were true does not make it true. Let's see if it is true, or if we have any hope of establishing that it is true. Consider a function gamma of x continuously differentiable. Yeah, suppose gamma of x is such that over an interval a to b, gamma of x times g of x dx is equal to 0 for all g belonging to the class of continuously differentiable functions. You understand that from the shorthand notation, when I write C1, it is basically continuously differentiable functions over the interval a to b, spitting out a real number. Okay, all of that is implied. I am just writing a shorthand notation here. The claim is then okay. So indeed it is true, is what we are claiming. The role of gamma is being played by this. Why is this true? Why should we believe this is true? Well, we can prove that it is true. Let us assume the contrary. Suppose not. Suppose not. So you have an interval a to b here, and suppose at some point, so I am not writing this proof in its entirety, I am just giving you a sketch of the proof. Suppose at some point say x hat, yeah, that is at x is equal to x hat, gamma x hat is not equal to 0. So let it be something positive without loss of generality. You might as well take it negative, doesn't matter. Let it be positive. Now because gamma itself, okay, I have not written it here, but gamma itself is also a smooth function, a continuously differentiable function. So if it has a non-zero, say positive value here, in a small neighborhood around it, it cannot suddenly disappear. Yeah, at least it's a continuous function, it cannot suddenly vanish. So therefore, let us say this is a subinterval, say C to D. Okay, so C to D is a subinterval in which say gamma x hat is greater than 0. This is without loss of generality. Then there exists C comma D such that CD is contained inside AB and gamma x is greater than 0 for all x belonging to this interval C to D. Okay. So the moment here's the claim. You are claiming, let's suppose this is not true. Therefore, there exists a point at which it is non-zero. Let it be positive without loss of generality. You will see at the end of the proof, even if you take it to be negative, the proof can be suitably tailored. Okay. Consider Gx is equal to x minus c whole squared into x minus d whole squared at, or rather for x belonging to the interval c to d and 0 elsewhere in the interval a to b. Can you check whether this is continuously differentiable? It would be, right? If you differentiate this once, it will still have, because it has repeated roots, so it will still vanish. The derivatives will also vanish. There are repeated roots, so the first derivative also vanishes at c and d. And if you stitch it together with the 0 function in the interval a to c and d to b, you can at least get a smooth stitching together, smooth up to the first derivative. That's the reason I took the square here. And what else can you say about the magnitude of this function or the sign of this variable in the interval c to d? Positive. So this is a continuously differentiable function, and therefore when you choose such a g here, this must also vanish. The question is, can it possibly be true? See, this function g is like a filter. It is picking out whatever business is being carried out by gamma in the interval c to d. Outside of the interval c to d, it doesn't care. And I have already seen that this gamma by my choice is a function which lights up at some point x hat in the interval c to d, and therefore no matter howsoever small that c and cd interval might be, at least in that small little interval, it assumes only positive values. So a positive value being multiplied by g of x in that interval is going to lead to a positive integrand, right? So therefore this integration cannot vanish. You can write that down in your own words here. The basic calculation or the basic choices have been already laid out here. The remainder of the proof is just about arguing that with this choice of a continuously differentiable g, such a gamma which suddenly showed a non-zero value at some point in the interval a to b could not have led to a zero integral or met this condition. Means that whenever you pick out a particular point where gamma fails to be 0, I will always be able to find a continuously differentiable g such that when you multiply gamma with that continuously differentiable g and you integrate this over the interval a to b, it will guarantee that that integral will not be 0, in fact it will be positive. Same thing if it were negative, well you could have just changed the sign of g, put a negative sign ahead of it, so that again the integral will be positive. Yes?
We select some other g, then we can like.
Yeah, but the point is, see, the condition here was that this must be true for all vanishing perturbations g that are continuously differentiable. So you have to understand the reasoning, the way it's carried out. The reasoning is carried out in this manner. If something has to be true for all g and you find something that's true only for a small class of g, that does not take anything away from the result. Rather the other way around, if I can always show that there will always exist a g, the moment this fellow fails to be 0 at a certain point in the interval, there will always exist a continuously differentiable g. And look, this g that I have chosen also vanishes, right? At a and b, by the very choice of this fact that there is 0 elsewhere in the interval, it vanishes, it's a vanishing perturbation. So there does exist a vanishing perturbation that actually ends up violating this tenet the moment this fellow inside this red box here fails to be 0 at any point, which then brings us to the celebrated Euler Lagrange condition. I hope this part is clear. Even though this is something I have done later, I would like to erase this because this part is more important. It's clear? Okay. So therefore we have and just like that we have arrived at a pointwise condition on optimality. Might not seem like much as of now, but there is a very interesting little physical interpretation to this. One that is very intuitive and we shall revisit again before the course is done. If you take an optimal trajectory or an optimal path or an optimal curve, any small segment thereof must also be optimal. Yeah? You could not have lost the semi-finals and qualified to the finals. At every point you must have done your best. But the other way around is not true, clearly. If you take small little optimal segments and stitch them together, the overall segment might not be optimal. Right? You take, for example, a triangle, a right angle triangle. You travel along the base and you travel along the perpendicular. Both of those are straight lines, optimal curves, straight lines on simple constant speed frameworks are optimal paths. But clearly to go from A to C, the hypotenuse would have been the optimal path. So do not be under the misapprehension that you take small little optimal paths, stitch them together, you get an optimal path. But the other way around is true. If I already give you the optimal path, then between any 2 points on that optimal path, you could not have done better than the optimal segment. And therefore it is but natural that this thing that is globally true for this entire interval now folds back. So this is something that is globally true. The interpretation is that this is locally pointwise true in a small neighborhood around every point x. Okay, so it's a transition from the global result to a pointwise result, but it's also something that's telling a very important property about optimality itself. The fact that any small segment of an optimal path must therefore needs also be optimal. Yeah, so that is one important interpretation that you should bear in mind. When we come back next, we will look at some special cases of this Euler Lagrange equation. So this is the celebrated Euler Lagrange equation. When we come back, we shall see that suppose there are some special features of this cost function j given by the Lagrangian. Special case meaning when the Lagrangian does not explicitly depend on x. Of course, implicitly, because y is a function of x, it depends on x. But if the Lagrangian does not explicitly depend on x, can we say something special about this condition? And by the same token, if the Lagrangian does not explicitly depend on y, can we say something special about this Euler-Lagrange condition in that and that sort of a setup? Those are the two things we shall see, and then we shall again go back to the Brachistochrone problem, and this time we shall actually get our hands dirty and solve a differential equation to arrive at the equation of the Brachistochrone, which is essentially that of a cycloid. Yeah. So all of that we shall see in the next lecture. Before we actually sort of close this today, just one more subtle point. If you have come across these terms such as momentum and Hamiltonian, if you haven't, don't worry, we'll talk about it as much as is warranted in this course. The Hamiltonian is going to be an incredibly important object in our course, so we'll obviously be dealing a lot with it. But we shall see that those two special conditions, when x does not explicitly appear in the Lagrangian or y does not explicitly appear in the Lagrangian, they correspond to trajectories or paths along which either the momentum remains constant or the Hamiltonian does not change. So those are some of the special features that we will extract out of this condition. Okay, thank you.